In April 2025, China introduced export restrictions on 7 heavy rare earth elements. The impact was immediate and physical. Suzuki Motor Corporation was forced to suspend production of the Swift at its European and Japanese plants. They didn't face a price hike, they simply ran out of materials to build their motors. This production halt moved rare earths from the realm of procurement costs into the realm of state-controlled logistics. For manufacturers, the availability of materials is now tied directly to diplomatic relations. For decades, manufacturers structured their supply chains around price volatility. Now, the primary risk is a targeted, physical deprivation of the specific elements required to keep a factory running. The rare earth supply chain is no longer governed by the economics of free trade. It is dictated by national security. When faced with these supply shocks, the industry response is often geologic, the belief that we simply need to dig more domestic mines. This is an aerial view of Minamotorishima Island. In 2026, Japan began continuous extraction tests of deep-sea mud off its coast, attempting to leverage vast underwater deposits as a domestic resource. This is raw, unprocessed rare earth ore. Despite the difficulty of locating these deposits, digging this rock out of the ground is the most basic, least technically demanding step in the supply chain. The true choke point is the midstream phase. It requires complex chemical separation, followed by a downstream metallization process, where those separated elements are turned into usable industrial alloys. A nation can possess mountains of rare earth ore, but without the industrial infrastructure to process it, that rock is strategically useless. Global monopolies in rare earths are not created by geologic luck. They are engineered through complex, high-friction chemical processing. The elements we call rare earths are not actually rare. The chemical problem is that they are near identical. In nature, they blend together, and they fiercely resist being separated from one another. To pull them apart, engineers use solvent extraction, forcing dissolved elements through hundreds of mixer-settler tanks, repeatedly washing them to achieve commercial purity. This physically massive midstream separation accounts for up to 8. China spent decades absorbing those environmental and capital costs. By subsidizing the infrastructure and tolerating the pollution, Beijing centralized global refining within its borders. Today, China controls approximately 90% of the world's rare earth refining capacity. That control is tightest for heavy rare earths, specifically dysprosium and terbium, elements critically required for heat-resistant permanent magnets used in electric vehicles and defense systems. Look at these finished magnets. China didn't stop at refining. They aggressively integrated downstream. They now manufacture 94% of the world's high-performance permanent magnets. China's strength lies in operating a fully enclosed, state-backed vertical industrial ecosystem from dirt to engine. If the vulnerability is this clear, why haven't the United States, Australia, or Japan simply built their own versions of China's ecosystem? This is the Mountain Pass mine in California. The U.S. possesses mining capacity and capital, but has virtually zero midstream processing. They are currently shipping raw ore back to China for separation. Australia has a massive resource base and is building primary processing, but they lack the downstream industrial base to manufacture the final magnets. Japan has the exact opposite problem. They lead in magnet engineering, but without domestic extraction or separation plants, they are severed from the upstream supply. Individually, Western supply chains are structurally fragmented. For any single nation to achieve total rare earth independence is a mathematical impossibility. The cost of building a standalone rare earth hub is immense. Replacing just 30 to 40% of China's current capacity is estimated to take 15 years and $25 billion. The alternative is an allied division of labor. This strategy creates an integrated pipeline. Australian primary processing handles the upstream, U.S. capital supports the midstream, and Japanese engineering dominates the downstream. Corporate alliances are already executing this blueprint. Lynas processes ore backed by Sojets. The U.S. funds MP Materials to rebuild separation, while Iwatani secures downstream supply. Free markets alone cannot compete with a state monopoly. This trilateral pipeline requires government intervention, including price floor guarantees and long-term offtake agreements. The solution is not matching China factory for factory. It is binding 3 allied economies into a single state-supported supply network. This trilateral architecture is moving on a multi-year timeline, accelerated by the physical supply shortages of 2025. 2026 marks the scale-up of magnet recycling ventures, driven by partnerships like the heavy rare earth agreement between France's Kermag and Japan's Iwatani. By 2027, non-Chinese refining capacity, such as Iluka's Eniaba plant seen here, is projected to finally come online to feed the downstream market. The objective of this alliance is not zero reliance on China. The goal is to create a baseline insurance pipeline, enough secure supply to keep critical factories running during an embargo. For corporate strategists, the directive is clear. Instead of waiting for geologic miracles, aggressively secure offtake agreements with these emerging midstream nodes. The geopolitical materials war will be won not by the nation with the deepest mines, but by the coalition that builds the most resilient chemical pipeline.